Hello, Science 30s. Today we're going to start with Unit D, and we're starting our new unit on energy and sustainability. We're going to jump a little bit out of order if we're following textbook, and we're going to actually start with chapters 1.4, and we're going to jump right into nuclear energy and how to calculate it. This way, we can allow ourselves the most time to practice some of these equations that we're going to learn and the ideas, and we'll have time to kind of let it soak in throughout this chapter. So what we start to see now is energy releases. And when we're looking at nuclear energy, we have three different types of energy radiations. First one we're going to talk about is alpha, next is beta, and then we have gamma. And this is what we already looked at last chapter, and this is what fell under the electromagnetic radiation or the EMR spectrum. Here, right from our data booklet, you can see that there is actual alpha particles and what it exactly is. And it's a helium nucleus. And we're given the exact kind of measurement of it, how it's denoted with that little alpha symbol. And it actually has a mass with it because helium does have a mass. A beta particle, and what we see is essentially a electron. And you see how it's denoted, and you see the mass of what the beta particle or electron actually is. On the other side, you see other subatomic particles or the radiations and their masses, or as you see that gamma radiation has no mass, and it is purely just that energy. And this is all again from your data booklet in page 8. So how does this all work together? And how are we going to see questions? Because we're not going to go into great detail about it, but we're going to start to introduce the ideas of these different alpha decays, beta decays, and we're going to start to understand some of the general principles of the energy around it. To start, we're going to be given very specific scenarios, and we're going to be told a lot of information, but we'll be able to figure things out from there. So we're given an element, americarium, and it undergoes alpha decay. So we're told exactly what is happening. And so remember that alpha particle is just helium. And so we see right there, it's going under alpha decay. So that means that americarium is actually breaking apart, losing a helium, but then what else is it losing? We have to remember also, though, that unknown, that AZX, what is all this? Well, we have this nuclear notation. So it's a little bit different than what we normally see from our periodic table. But what we have at the very top is our A, and that's going to be our mass number. And so it's harder to see when you're dealing with something like oxygen or helium. It's, is it mass number? Is it proton number? If it was a mercurium, you're very obvious. There is no atomic number of 241. So it gives it away that that is the mass. Okay? For this nuclear notation, though, we just put the atomic number on the bottom instead of the top like we're used to, but we put the mass up top. And then we have our element symbol. So what we'll see, I've taken it right from our periodic table, is americarium. And what we see is it has a atomic number of 95. And then what happens is helium breaks apart, and helium takes away two of these little protons. What we see here, and we see it here. And so what's actually happening is americarium is losing two protons. It is changing what the element is. These are nuclear reactions, not just a chemical reaction where the chemicals and the elements stay the same. This is nuclear where we're actually changing the elements. And we're also changing the mass numbers too. So it's going from 4 up top, and we're taking it away from 241. So what do we actually make? Well, we can simply go 95 here over on this side. Remember, this is essentially an equal question because we're always going to keep it in balance. 2 plus what? And so we're going 2 plus what equals 95? Or we can go 95 minus 2, and well, we know what happens is it equals 93. And when we look up on the periodic table, the atomic number 93, we get Neptunium. And now we figured out what the other element was part of this nuclear decay. So we've broken it apart, had this alpha particle break off, and newtonium was formed. So we just saw a reaction where we split apart the element. And what exactly is nuclear fission? Well, it was exactly that. It involves splitting apart atoms and we're breaking apart elements. These are not chemical reactions where we're creating new chemical substances, but the elements stay the same. This is where we are actually changing the elements on the nuclear level. And so large atoms, something like uranium, is going to be one of our very typical examples because it's so large and it goes through many decay processes and it breaks into many different things. And we're just going to look at it simply, but it's hit by a neutron and it breaks its nuclei into smaller bits. And it just doesn't do it as one jump, but we're going to see it through different several stages as it goes. With these breaking apart of these elements, there is large amounts, and not just like a large amount, like burning a lot of oil and coal, it is millions of times larger than that. And we have this little graphic, the difference between fission, and probably a lot of people have heard actually about fusion and nuclear fusion. There is a difference. They're very close, but fission is creating a fissure and we're cracking apart these elements and we're getting a bunch of energy after these two elements are formed. Fusion is where we're taking two smaller ones and we're making something larger. So here we have nuclear fusion, where we're actually going to take two smaller nuclei and we're going to form a larger nucleus to release even larger amounts of energy than that what we saw in nuclear fusion. And what we see with this fusion is the same reaction that happens in our sun. We take two hydrogen atoms and we collide them. Well, we don't collide them, but the sun and the reaction in the sun collides and it makes a helium element, forming a massive release of energy. So now we've been talking about these reactions, and the big key is that they release massive amounts of energy. And the important part is, how do we get electricity and how do we control these reactions? Well, the energy released from a nuclear fission reaction is used to boil water that surrounds that nuclear fuel. If you think about it, it's the very kind of similar processes of burning gas, burning oil, burning coal. We use it to heat up water, and we use this boiling water to turn a turbine. And this high pressure steam that comes from it, it just spins and it spins that generator, which we talked about last unit, and how we actually generate a coil of wires moving through a magnetic field to make electricity. On the very simplistic diagram of it, we see that a generator, as we can see here, gets all this pressurized steam from inside the nuclear reactor tower, and that steam pushes through a turbine, and then that turbine spins very, very fast. The turbine spinning generates electricity, and then the water is returned to the system. And it's important to note there is two separate tanks of water. The two waters never actually mix. So the water that's used inside the nuclear reactor never is actually exposed to the water that is used in the cooling stations. And so when we see those big towers that you saw from The Simpsons, those are actually just to cool the water that cooled the other water that went inside the nuclear reactor. So we're not having nuclear water spill out from these nuclear reactors. So how do we control these reactions? Well, in Canada, we have this special reactor called the CANDU nuclear reactor that uses this uranium-235 as fuel. Coming back to uranium, this is the example we use because this is the example we use in Canada. This requires neutrons and This essentially requires a neutron gun that regulates the amount of reaction energy that is actually happening. And then we use water to also control how fast these neutrons are spreading around. We use this term called heavy water to slow down these neutrons to form proper collisions so we can actually control the nuclear breaking apart of this uranium so we can actually harvest and not just have this huge nuclear reaction get out of hand on us. This is an example of the CANDU reactor that's used in Canada, and you can see right at the very bottom where we have the heavy water moderate the reaction happening. And you can see the nuclear fuel bundles in yellow down there inside the nuclear reactor. And we have the heavy water. And then you also have the coolant that is separate from it that actually has the running of the heavy energy. And then it goes into the steam generator. And you can see there's different pipes and keeping the water separate from each other, all contained. And then out comes electricity. So I said the CANDU is a Canadian design. So if you kind of clued in, the CAN is for Canada, and the D is actually not part of Canada, but it stands for deuterium, and then it's uranium for the U. But the heavy water has a higher density, and so this deuterium is actually a isotope of hydrogen. And so hydrogen normally has one proton, one electron, has a mass of 1, no extra neutrons. However, this deuterium actually has a mass of 2, and that's what you see up here. Remember, this is nuclear notation. So at the top we have the mass, and at the bottom we have the atomic number. So it's still hydrogen. However, it is hydrogen with one proton and one neutron, and we call this heavy because of the doubled mass essentially. And we call this special hydrogen deuterium. So why is this so important? Because a nuclear reaction actually is a chain reaction. And so this is dangerous because the fission of uranium is a uncontrollable reaction if we don't actually control it. Because what happens is one neutron is used to break apart the uranium. However, when the uranium breaks apart, and at the end result, it actually sends out 3 more neutrons. And those 3 neutrons can then collide with another 3 uranium elements, and those 3 can break apart, and then all of a sudden those 3 release 3 each, making it 9, and then 9 produces 27, making it a out of control nuclear reaction. So this is why it's very important that we can actually control nuclear reactions. A case would be Chernobyl. I know there's HBO series called Chernobyl, and there's lots of information coming out about what happened in Chernobyl, and there's a lot of different things coming up now where people are actually going on tours to Chernobyl. While it's still a hot zone, people are kind of taking the risks and going to see what actually happens when a nuclear reactor becomes uncontrolled. Here's a quick little graphic to help kind of explain the point where you have one neutron coming in, hitting that uranium, making it uranium-236, splitting apart just like we saw with barium and krypton, but when those come out, we get 3 neutrons coming out. And then from those 3, we get another 3 breaking off to get our 9. And it's not always the case. This is just one example. Sometimes it's 2, but in this case, we're seeing 3 splitting to 9 and then into 27 and so on. So this is why it's very important to have this heavy water to help control how these extra neutrons are coming out.